Hello everybody and welcome to this lesson in which we are going to learn more about dynamic arrays. We are going to see what dynamic arrays are, when they are used, what are the main advantages and disadvantages of them, and of course what happens behind the scenes when we are using a dynamic array. So let's start with the definition. A dynamic array, or how it's also called resizable array or mutable array or array list, is a random access, variable size list data structure that allows elements to be added or removed. So the main difference between a dynamic array and a static array is actually here, variable size. Remember, when we wanted to use a static array, when we allocate that array, we need to provide the constant size that that array is going to have throughout its lifespan. Here, we don't need to do that. We can start with an empty dynamic array. And as it says here, we can add and remove elements on the run, and the size of our dynamic array is going to be adjusted accordingly. The dynamic array, it is supplied with standard libraries in many modern mainstream programming languages. For example, in C++, it is called vector. In Python, it is called list, and it has this syntax. And in JavaScript, it also has this syntax, but is called array. And the third point here is that dynamic arrays overcome a limit of static arrays, which have a fixed capacity that needs to be specified at allocation. This is what I told you earlier, and this is the main purpose that we are going to use dynamic arrays over static arrays in a lot of problems, because the number of objects that are going to be stored in an array might be unknown in a lot of cases. And of course, we don't want to allocate a static array which has a size equal to the upper bound of those objects, and that upper bound could be so huge, right? But don't worry, we are going to talk about this in a minute. Now let's take an example to see how the dynamic array really works. For this example, I am going to use a dynamic array which is named nums and initially is going to be empty, and also let's suppose that I'm just going to insert integers in this array. Awesome. Now, when the computer sees this line of code, it thinks like this. Well, he's probably going to use this dynamic array. And how do you use an empty dynamic array? You don't. So he is probably going to push at least one element in that array. So once that first element is pushed, I need to be ready for that. And how can I get ready for that? Well, of course, I'm going to need to allocate the memory in order to store that element. One thing that I should mention here is that even that dynamic arrays have a variable size, they still use a contiguous zone of memory in order to make those operations like random access and modifying an element in constant time. And because the computer doesn't know how many elements I will actually push in that dynamic array, it doesn't want to get too crazy and let's say allocate memory for 100 integers when I might only use 1 or 2. So just to be safe, it's gonna look for a contiguous segment of memory of size 1 integer, right? So 4 bytes. Let's say it found it here. Cool. It's going to, of course, point my array nums to that zone of memory. So nums, this is your zone of memory by now. You can use it. Nobody else is going to access it. And what happens here, because you notice this capacity of nums, each dynamic array has a property called capacity, which basically means how many elements it will be able to store at most at some moment of time. So basically the size of the contiguous segment of memory that is allocated for the array. For now, it is 1. Cool. Let's say I will push the element 2. Now my array nums is 2. What happens? Well, the computer is going to write the value 2 in my one and only chunk of memory. I move on and let's say I push the value 3 into my dynamic array. So the array nums should now look like this, 2, 3. Now, the computer knows that the capacity of the array is 1. And this is a problem because I don't have any memory left in my contiguous segment, so I'm not going to be able to store the new element. In this moment, it knows that it should look for another contiguous segment of memory that will be able to store at least 2 integers. So what's going to happen is that it will eventually find that zone of memory. Let's say it is this one. It will point nums to the new zone of memory. So basically tell the dynamic array, this is your new zone of memory. Use this however you want. But it also needs to make sure that the values in these spots are the right ones. Because remember from the previous lesson, each time we allocate a new zone of memory, the value there is going to be unknown, right? So it might be something random. We don't want that. So first of all, it has to copy the contents of the previous segment of memory into this new one. In this example, we had only one element, so this element is going to be copied here. Then it is going to assign the value 3 to the next spot, which is this one. And then also, because we don't need this memory anymore, it is going to release the memory for maybe other variables or arrays to use it. Now, the capacity of nums is 2, and we can move on. Let's say I'm going to insert next the value 4. So my array nums should look like this, 2, 3, 4. The computer looks at the capacity, oops, it's 2, so I don't have enough memory to store another variable. What should I do? Of course, I'm going to find a contiguous segment of memory which is able to do that. So a contiguous segment of memory which can store at least 3 integers. But this is the nice part. It's not going to look for a segment of memory of size exactly 3 integers, but at size exactly 4. So the capacity doubles every time. The computer will eventually find it. Let's say it's this one. Sorry about my awful drawing skills. Now, it found a contiguous segment of memory of size 4 integers. What's gonna do? It's gonna point the array nums to this new zone of memory. Then, it has to make sure that we copy all the contents from the previous zone of memory into the new one. So this 2 is going to be copied here. This 3 is going to be copied here. And of course, then pushes the new value here. And this is how the new array looks like. And last but not least, we are going to release this zone of memory as we don't need it anymore. So also remove this zone of memory. Now, the capacity of nums is 4. It just doubled. And as you can see, for the first time, we actually have some unused memory here, which we are going to use in the future to store the next element that's going to be pushed in the array nums. So again, let's say the new element is 5. When I want to push 5, I take a look at the capacity, 4. This is nice, 4 elements for capacity, I can do it. So I just assign the value 5 here. Now let's say I want to push another element. I want to push 6. What's going to happen? Well, now the size is 5, the capacity is 4. This is not good, so I will need to find a contiguous segment of memory that supports at least 5 integers. And as I said, it's not going to find one with size exactly 5, but it's going to find one with size double the previous size. So the capacity always doubles. So the next capacity is going to be 8. It's going to look for a contiguous segment of memory of size 8. Let's say it's this one. It is going to point the array nums to this new contiguous segment of memory. Then it's going to copy all the contents from here into here. So 2, 3, 4, 5. Then it's going to assign the new value into the next spot, 2, 3, 4, 5, 6. And of course, it's going to release the memory. Now, this is how our dynamic array looks like. Now we have 3 unused spots of memory, which we are going to use for the next 3 elements. And of course, the capacity is 8, right? So, as you probably can guess, if I try to, let's say, push 7, 8, and 9, then I don't need to do all of these, look for a zone of memory, copy the contents and all that stuff. For each of these new elements, I already have the memory to store them. And this is what happens behind the scenes each time we push a new element into a dynamic array. If the size of the array is less than its capacity, which means we still have some unused memory, at least for storing one more value, and this is what we are going to do. Nums of size becomes equal to the new value, and of course the size of the array is getting incremented. Else, if the size of the array equals its capacity, then we need to allocate a new segment of memory, which will have now a size of 2 crossed capacity objects, right? In this example, the objects are integers, but could have been strings, could have been maybe objects defined by us, and so on and so forth. Then we are going to copy the contents from the previous segment of memory into this new one. For example, here, 2, 3, 4, 5 are being copied in the first 4 spots here. Then we will release the previous memory as we don't need it anymore, and maybe another data structure is going to use that throughout our algorithm. And then the 4th stage, now we indeed have the new zone of memory. We indeed have at least one spot to store the new value. So this is what we are going to do. And then the size of the array gets incremented. And you are probably asking yourself, Andy, why do I need to know all of this? Why don't we just learn how the dynamic array works and then move on? Well, this is interesting. Let's actually analyze the time complexity of this algorithm each time we push a new element. So, if size is less than capacity, of course, this is constant, no problem. Then we have an assignment and the size gets incremented, also constant, no problem with this. But now here is the big thing. Else, which means the size equals capacity, we first allocate a new segment of memory of 2 crossed capacity. So, for allocating a segment of memory, we are going to need big O of the size of that segment, time and memory complexity, right? So performing this first stage already takes big O of the size of the array. Then we have to copy the contents, which is also big O of the size of the array. Release previous memory. Yeah, the segment contains size elements, so still big O of size. And then this is an assignment and we increment the size, which is constant. So these all 4 steps are big O of the size of the array. And we are discussing about this because most of the people just know that pushing a new value into an array is constant time and don't care about the mechanics behind it. Well, this is important. Notice that each time the size equals the capacity, we are actually doing big O of size time complexity. And that's not only it. This big O of size here happens actually in the best case scenario like this one, where our objects are integers. And guess what? Integers are very easy to copy. It takes constant time to copy one integer, or deleting. For example, when you need to release previous memory, you are going to need to delete that integer from the memory. That's also constant. But imagine you work in a company and imagine you are using a dynamic array to store some objects which are defined by yourself, right? And those objects are actually more complex than just integer. Let's say you have an object, right? A class, you define a class, and this class, I don't know, stores inside it maybe 100 integers. So 100 integers and maybe, who knows, 500 characters. It's just an example, right? When size equals capacity and you need to do all of these steps, now you will have to allocate a segment of 2 crossed capacity objects. So 2 crossed capacity crossed how much memory one object needs. And as you can see here, it needs 100 integers and 500 characters, which is way bigger than only one integer. Then you will have to copy the contents from this segment to this one. Copying an integer again is simple, but copying an object like this actually requires copying 100 integers and 500 characters. Release previous memory. Deleting one integer was simple, but deleting an object like this requires actually deleted 100 integers and 500 characters. You see what I'm saying? The dynamic arrays have the disadvantage that the cost of resizing themselves is actually dependent on how complex the objects that you are going to store in this dynamic array are. In most of the coding problems that we are going to solve, we will store integers inside our dynamic arrays. But let's suppose we have a problem in which we want to store some strings. Let's say in our dynamic array, we store strings of length L, right? So strings of some length, which we know is equal to L. When you store strings of length L, to copy a string of length L is actually big O of L. And so is to remove one or to allocate L characters just to store a string. So actually, instead of big O of size, you are going to have big O of size crossed L each time you need to do all of these stages. So instead of big O of 1, that is the time complexity everybody knows it takes an element to be pushed into a dynamic array, now if you have, for example, a string like this, it's going to be big O of L actually. Or if you have another object, it will depend on the size of that object. Now let's move one step back and actually talk about dynamic arrays that hold integers. And now that we know how the dynamic array works, And we know that not always when pushing an element, we are going to have big O of 1. It could be either big O of 1 or big O of size. I actually want to explain to you why it is considered that on average, the cost of these types of operations is big O of 1. Because it is, but we need to use the amortized analysis to show that. And to do this, I'm going to take an example in which I start with an empty dynamic array, and I'm going to push n integers one after another, and we are going to see how the size, the capacity of those arrays changes, and of course, what is the number of iterations on each push. So, the first time I push an element, because the size is less than the capacity, everything is fine, I have enough memory, so the size is now 1, the capacity is now 1, and we just did that assignment, so the number of iterations is 1. Then, on my second push, size equals capacity. So we need more memory. So we are going to do all those stuff, right? Find a new segment of memory of size 2, copy the contents, release that memory, and of course the capacity is going to get double after this. The size is going to be 2, and the number of iterations is big O of size, and the size of the array when we did that was 1. And I'm going to mark this with an arrow, just to remember that this was a scenario in which the size equals capacity and we need to do all of those extra stuff. Now, on my third push, what happens? Size equals capacity. So we do all of those. The capacity doubles. The size is now 3 as we have one more element. And the time complexity for this is the size of the array, which was 2. And this is also an arrow. Now, on my fourth push, the size is less than the capacity. Nice. So we have memory. All we do is an assignment. So here we have 1. Nice. Then on my fifth push, what happens? Size equals capacity. So I do all of those. The capacity gets doubled. Now the size is equal to 5. And the number of iterations is the size of the array, which was 4. And I also have an arrow here. Then on the sixth one, what happens? Size less than capacity. Size became 6. Capacity still 8. We just did an assignment, so 1. This is also going to happen on the 7th and the 8th pushes, right? So for those two, I can also write size 7, capacity 8, 1 iteration, size 8, capacity 8, 1 iteration. And now on my 9th push, size equals capacity. We have to do all that extra stuff. The capacity gets doubled. It's now 16. The size gets increased, is now 9. And the number of iteration is, what was the size of the array? 8. And we have an arrow. And then, of course, we are going to have a couple of ones here again for 7 times. For the next 7 pushes, I'm still going to have 1 iteration and so on and so forth. So what I want to show you here is that for the most of the time, the size will be less than the capacity. And all we are going to do is just 1 iteration, right? This happens most often. But there are these scenarios in which this doesn't happen. And how many iterations we do? Well, first time we do 1 iteration. The second time this happens, we do 2 of them. Then we do 4 of them. Then we do 8 of them. Oh, you see any pattern here? Each time this happens, the number of iterations that we do just to, copy, release the memory, find a new memory segment, doubles. Okay, so if we were to count the total number of iterations, because of course the total number of iterations is going to give us the final time complexity of making n pushes, when we count the total number of iterations, this sum represents the total number of iterations when we start off with an empty dynamic array and we make a total of n pushes. Now, notice that when I've written this sum, I have grouped the number of iterations by the scenario in which they happened. All of these are the iterations that happen on that second scenario when size equals capacity, and all of these are the ones that happen when size is less than capacity and we only did an assignment. This is a geometrical progression and actually has a formula. It is equal to 2 to the power of k plus 1, all of it minus 1. If you don't know how to compute this, don't worry, it's super simple. All you need to do is add another 1 here, and if we do that, what's going to happen? 1 plus 1 equals 2. 2 plus 2 equals 4. 4 plus 4 equals 8. 8, and so on and so forth until on the last one, you see 4, 8, 2, 4. We're going to have 2 to the power of k plus 1. And of course, because we have added an extra 1 which wasn't there, we are going to subtract it in the end. So this is a fun way of getting the formula for this sum. So this sum is equal to this. But one more interesting thing here is that remember, all of these were sizes, right? Big O of size, big O of size, big O of size. And because they were sizes, what is the maximum size that our dynamic array will take? Of course, n, because we did n pushes. So this 2 to the power of k is actually less than or equal to n, which means that if I multiply this by 2, I get that 2 to the power of k plus 1 is less than or equal to 2 crossed n. So this is actually less than or equal to 2 crossed n minus 1. Less than or equal to 2 crossed n minus 1. Now, in the second sum, for how many times do I add 1? Well, this is pretty simple. We had a total of n pushes. And as you can see here, I start from 2 to the power of 0, and I get 2 to the power of k. So I have k plus 1 terms here from the total of n, which means that here I'm going to have n minus k minus 1 terms, which again, let's say this is of course less than or equal to n. So we have n from here, 2 crossed n minus 1 from here. So this sum is less than or equal to 3 times n. So we can conclude that the total number of iterations that will be performed when starting with an empty dynamic array and pushing n elements one after another into it is less than or equal to 3 crossed n, which is, in terms of time complexity, big O of n. Alright? So, if for n pushes you get a big O of n, this is why people say that on average, each push or removal, it's the same, is constant time. And this is it, guys. I hope you enjoyed the lesson. Now you definitely know how a dynamic array works, when it is needed, and finally, why this time complexity is really big O of 1 on average. I'll see you on the next one. Bye.